Okay, so in this session we are going to talk about dimensionless variables in greater detail, and we'll see how they make the foundation for well testing. So first, what we'll do is we'll derive the constant terminal rate solution as we did in the solutions for RD presentation. But first we'll do it for transient state. We did not derive the solution of RD for transient state in the previous solutions of RDE discussion. But now we will look transient state into greater detail. And basically in this session we will be considering a reservoir with closed boundaries, closed no flow boundaries. So in such a reservoir, when the production rate is changed at the wellbore, first the reservoir is in transient state and then it goes into, so basically it means that pressure disturbance is now traveling through the reservoir. So before that disturbance reaches the boundary, there is transient state. When the disturbance has just reached the boundary, then the late transient state starts. It continues for some time, and then finally when the flow is stabilized, means at all points in the reservoir the rate of dP by dr, that is the pressure gradient, is constant at all points. So then the semi-steady state is achieved. Okay, the rate, however, remains constant. This is the surface flow rate; it remains constant, and you can see how the pressure behavior with the PWF. Initially, PWF was equal to PI, that is the reservoir pressure. Okay, so there was no flow. Then PWF is started to means basically we are starting to produce. So PW produce on the reservoir. Okay, and that we control from the surface, from the choke line. Okay, so we set a rate at the surface that okay we have to produce at this rate, and then the PWF, that is the flowing bottom hole pressure, starts to decline gradually, and then PI minus means the reservoir pressure minus the bottom hole flowing pressure, that's called the drawdown. Okay. So the pressure response can be divided into three sections depending on the value of flowing time, reservoir geometry, and part of the reservoir being drained by the well. And we saw those three parts in the previous slide. They are transient, late transient, and semi-steady state. Okay, so now the thing is the value of flowing time. It means when you start producing from the reservoir, first there will be transient state, then there will be late, then it will get into late transient state, and then finally it will get into semi-steady state, strictly in this order. Okay, so there is a time factor associated with it. Then again the reservoir geometry. The reservoir boundary may or may not be circular, or the well may or may not be placed at the center of the reservoir boundary of the radial cell. Okay. So reservoir geometry also needs to be considered, and the part of reservoir being drained by the well. That means in case of transient state, the reservoir appears to be infinite in extent because the pressure disturbance has not yet reached the boundary. So it is not draining from the whole entire reservoir. Okay, it is draining from some part of the reservoir. But in case of steady state, semi-steady state, the whole reservoir is being drained. Okay. So we will discuss transient flow in more detail. So no boundary effect on the pressure response. One thing to remember is that we can only measure the PWF, the flowing bottom hole pressure at the well. We cannot measure the pressure anywhere in the reservoir. Okay, so basically what we'll be doing is we will be speculating what will be the pressure there. Okay. So we are after changing the flow rate, we are measuring the pressure response at the well. Okay, so until there is transient flow, the effect of boundary will not be felt on the pressure response at the well. The pressure disturbance travels like a wave, which we have discussed in another session. Okay, so that wave is acoustic in nature, but the wave has not reached the boundary yet. Okay. So that wave has not yet, it has been generated by changing the flow rate at wellbore, but that wave has not reached the boundary yet. Okay, so the effect of boundary is not felt, hence the reservoir appears to be infinite in extent. So the initial and boundary conditions in this case will be P is equal to Pi at T is equal to 0, because before starting the production, PWF will be equal to the reservoir pressure. So that there is no flow. So the well is set, in that case, the well is set to be shut in. Okay. and P is equal to Pi at R is equal to infinity. The reservoir appears to be infinite in extent. Okay, so R is equal to infinity means infinity, and for at all times in the transient state, the pressure at the outer boundary, which is at infinity, would be equal to Pi, the initial pressure. Then limit R del P by del R with R tending to 0 is equal to Q mu by 2 pi Ks. This is the initial inner boundary condition. Okay, and this is derived by the Darcy's law. Okay, and limit R tending to 0 means since the reservoir appears to be infinite in extent, so the inner boundary, that means the wellbore, appears to be like a line, okay, compared to, so its radius is almost negligible compared to the extent of the reservoir. Okay, so like in current electricity, there is a from a line source. This is basically, we'll be deriving the equation of a line source, of flow into a line source. Okay, in current electricity, there is a line source of charge, so from that we measure electric field and everything. We will be doing something similar here as well. Okay, except this is for fluid. So all assumptions which we made during deriving the radial electricity equation, that apply here, which means liquid, the flow is liquid, completely liquid. Okay, and it's assumed to be incompressible. Okay, so we'll be using the linearized form of the radial electricity equation. Okay, so also the fluid itself must have a constant viscosity and small and constant compressibility. Okay, so we are basically assuming liquid flow, which means single phase oil. Okay, so under these conditions, RD will be in linearized form 1 by R del by del R, R del P by del R is equal to phi mu C by K del P by del K. This is the radial electricity equation in its linearized form. Okay, but then we can use a Boltzmann transformation. We introduce a new variable named S. S will be equal to R square by 4 into the electricity constant, which is equal to phi mu C by 4 kT R square. Okay, this K by phi mu C is called the electricity constant. Okay, we have seen in the previous session while we were discussing dimensional analysis. Okay, so we will be doing a substitution. Okay, we will be substituting R square by 4 R square by 4 D. There would be a capital D here dt by S. Okay, so hence del S by del R is equal to phi mu C R by 2 kT, and del S by del T will be equal to minus phi mu C R square by 4 kT square. And we are using D is equal to K by phi mu C, means D is the diffusivity constant. Okay, so therefore S is equal to R square by 4 dt, and del S by del R is equal to R by 2 dt, and del S by del T is equal to minus R square by 4 dt square. Now we will be substituting these values in the diffusivity equation. So del P by del R can be written as del P by del S into del S by del R. Okay, and del P by del T can be written as del P by del S into del S by del T. Okay, so del S by del R is R by 2 dt, and del S by del T is R square by 4 d T square. Okay. And then doing further calculations, 2 by R into del by del R square by 4 dt into del P by del S is equal to minus S by dt, and these are the calculations you should carry out on your own once. Okay, minus S by dt del P by del S. Plus R is taken here. Okay, so 2 by R term is taken here, so it becomes minus SR by 2 dt into del P by del S, and del by del R bracket R square by 4 dt becomes S. Okay, so S del P by del S is equal to minus SR by 2 dt del P by del S. So now the chain rule of differentiation is applied on the left hand side, so it becomes del S by del R into del P by del S plus S del by del S into del P by del S into del S by del R, and the right hand side remains same, minus S del S by del R into del P by del S. There might have been some rearrangement there. Yeah, right. Minus SR by 2 dt, that's equal to del S by del R. Okay. R by minus R by 2 dt, that's equal to del S by del R. So we are substituted it here. Okay, and plus del P by del S plus S del S by del P into del P by del S is equal to minus S del P by del S. Okay. So this is an ODE which can be solved by letting del P by del S is equal to P dash. Okay. So we let del P by del S is equal to P dash and put it in this equation. Okay. So it will become P dash plus S del P dash by del S is equal to minus S P dash. So 1 plus S P dash is equal to minus S del P dash by del S. So 1 plus S by S into ds is equal to minus dp dash by p dash. Okay, so we integrate both sides, we get ln p dash is equal to minus ln s minus s plus c1. C1 is the integration constant. Okay, so we take the exponent of the whole equation, so we get p dash is equal to c2, this is a different constant now. Okay, it will basically be e to the power c1, e to the power minus s by s. So we get s p dash is equal to c to the power c2 e to the power minus s. Okay, then from the inner boundary condition, limit r tending to 0, r del p by del r is equal to qb by 2 pi kh. Okay, so del p by del r can be written as del p by del s into del s by del r is equal to qb by 2 pi kh. So now we are changing the limit. Instead of r, we will be bringing s. So when r tending to 0, s also tends to 0. So limit s tending to 0, s del p by del s is equal to qb by 4 pi kh. So implies limit s tending to 0, s p dash is equal to qb by 4 pi kh. Whereas limit s tending to 0, c2 e to the power minus s is equal to qb by 4 pi kh. Whereas c2 is equal to qb by 4 pi kh, because we put s here can be equal to 0 here, it becomes c2. Okay, so this way we find the value of c2. I repeat again, it is highly recommended that you do these calculations on your own once. Okay, you will understand them better. I have shown the calculation steps here, but it is necessary that you carry out them once on your own manually. Okay. So now the equation becomes p dash is equal to qb by 4 pi kh e to the power minus s by s. Okay, so at any point at r, at t is equal to 0, s is equal to infinity. Okay, so because s was so to find the pressure at any point in the reservoir, we have to integrate the previous equation from pi to pr comma t del p is equal to q mu by 4 pi kh integral infinity to x is equal to 5 mu dq by kr square. Okay, so at t is equal to 0, s would be infinity. Okay, so we have to integrate from t is equal to 0 to a certain time. Okay, that was our objective. So we have to keep the lower limit as infinity, and then x is equal to 5 mu cr square kt. And inside the integration we to the power minus s by s into ds. Okay, employs p r comma t is equal to pi minus q mu by 4 pi kh integral. We have reversed the limits and then we have taken out a minus sign. Okay. So x is equal to 5 mu cr square by 4 kt to infinity e to the power minus s by s ds. This equation is the line source solution of the relativity equation. It gives pressure p r comma t as a function of position and time. Okay. So this integral on the right hand side, integral x to the power infinity to the power minus s by s into ds, where x is equal to 5 mu cr square by 4 kt. Okay, this integral is called the exponential integral ei. Okay, and if x 5 mu cr square by 4 kt is less than 0.01, so it can be approximated as eix is equal to minus ln x minus 0.5772, which is approximately equal to minus ln 1.781x. This 1.781 can also be denoted by gamma. This is the Euler's constant. Okay, which is e to the power 0.5772 is equal to 1.781, and this is the Euler's constant, which is denoted by gamma. Whenever you see gamma around here, it means it's Euler's constant. So for x less than 0.01, the pressure equation can be written as PRT approximately is equal to Pi minus Q by 4 pi kh ln 4 kt by gamma 5 mu c r square. And if we introduce the Van der Waals mechanical skill factor, Okay, and it is included as a time independent perturbation. It basically indicates wellbore damage, which is time independent. So the equation will become PRWF, how much is equal to Pi minus Q mu by 4 pi kh ln 4 kt by gamma 5 mu C RW square plus 2s. Then we see the late transient flow. So in late transient flow, the effect of boundary has been felt, and the late transient constant rate solution depends on shape of the area drain or the boundary shape, okay, and location of the well with respect to the boundary. Okay, now see why this is important is because uh, when the pressure wave is generated by changing the well flow rate at the wellbore, it travels in all directions. Okay, it goes radially upward. Okay, and with the same speed in all directions. Okay, so if at some orientation it will reach the boundary before, then at some another orientation it will reach the boundary later. Okay, so basically in all directions the boundary may not be reached at the same time. Okay, so that is why the late transient flow exists between the time when one of the waves, one of in the boundaries reached, in one of the closest boundaries reached, which would be in one of the directions, to the time when the farthest boundary is reached, which would be a later time. Okay. Until that time, late transient flow exists. Then after late transient flow, once all the boundaries in all directions have been reached, okay, so the stabilized well flow conditions will prevail. Okay. So rate of change of pressure with time becomes constant, and this corresponds to a semi-steady state flow. This condition occurs in case of closed no flow boundary. Okay. For semi-steady state condition, the solution can be obtained by adding the simplest material balance equation for the bounded drainage volume. Okay, which is equal to C AH phi. AH is the reservoir volume. Then phi is the porosity, so this is the pore volume in the reservoir. Okay, C is the compressibility. Okay, into Pi minus P bar, which is the average current reservoir pressure, which is equal to, and that is equal to Q. This is basically means the tank model. Okay, you are considering reservoir to be a tank, and you are extracting fluid out of it. Okay, so in time t, the volume of fluid extracted would be Q into T. Okay, where Q is a constant. Okay, so the volume of so this is the underground withdrawal. Okay, this is the underground withdrawal, and that would be equal to the volume produced in time t. Okay, this C is to account for that expansion, the compressibility of the liquid, because in the reservoir condition, the reservoir fluid will be more compressed because the pressure will be higher at that surface. The fluid will expand a little, maybe expand a little because of lower pressure. And then the semi-steady state flow equation would be P bar minus PWF is equal to Q by 2 pi kh half ln 4a by gamma C RW square plus S. We derive this equation and the solutions of RD discussion. So we can see from it. This is the generalized equation for this boundary of any shape, and we'll place that any location with respect to the boundary. Okay, so this addition will give us PWF is equal to Pi minus Q by 2 pi kh 1 by 2 ln 4a by gamma Ca RW square plus 2 pi Kt by phi mu Ca plus S. Okay, so P bar is the average reservoir pressure within the drainage boundary, and Ca is the breeze shape factor. Okay, now this equation is with respect to Pi. Okay, and now we will see how it deals the dimensionless variables. So in our dimensional analysis discussion, we have shown how these dimensionless variables are derived. Okay, which are RD, which is equal to R by RW. RW is the wellbore radius. Okay, and you can see how their dimensions are equal to 1, means their dimensions are basically m to the power 0, l to the power 0, and t to the power 0, which is equal to 1. Okay, so we have derived RD and TD and QD. We can check their dimensions, so they will all come out to the dimensionless, and how they are derived, that we have discussed in the dimensional analysis presentation. Okay, and how they are derived using by applying Buckingham Pi theorem on the radial diffuse equation and the equation. Okay, so these were in SI units in metric system. Okay, but we need them in field units as well. So this is how they look in field units. T is equal to 0.000 264 kT by 5 millisecond. RW for where T is in hour. Okay, if T is in days, then the coefficient becomes 0.00634, and TD that which is cannot be called a function of TD and RD is equal to why it is written, why dimensionless method is written this way, because it implicitly TD is implicitly a function of TD dimensionless time and RD dimensionless rate. Okay, however they do not show here, but it contains a TD and a RD term implicitly. Okay, so anyway in field units TD can be expressed as TD is equal to 0.00708 Ks by Q Pi minus PR comma T. So now we will put these variables in the equation, radially diffused equation of the linearized form of radially diffused equation, which will be 1 by R del by del R del Q by del R is equal to phi mu C by K del P by del T. Okay, so we write R as RW into RD. Okay, del by del R can be written as del by del RD into del RD by del R. Then on the inside in this bracket we write again R as RW by RW into RD. Del P by del R can be written as del PD by del RD into del P by del PD into del RD by del R. Okay. Wherever you see calculations in this entire process, it is suggested that you once do them yourself. You take the calculation step from here and then do them yourself. On the right hand side, phi mu C by K means as it is, and del P by del T can be written as del PD by del PD into del PD by del T into del P by del PD. Okay, so now we will pick the values of from here. Okay, so del PD by del T will be equal to 0.00634 K by phi mu CT. Okay, we are taking in the metric system for now. Okay, for now we are taking them in the metric system. Okay, so del PD by del T will be equal to this T will go over, it will be KT by phi mu CT RW square, and similarly del PD by del T will be equal to 2 pi Ks by Q mu only minus 2 pi Ks by Q mu. This is the pressure with respect to which we are differentiating. So now we have to substitute these values and we will simplify them. Okay, this is del PD by del P by del PD minus Q mu by 2 pi Ks, and then del RD by del R will be 1 by RW. Okay. So finally the equations which remains is 1 by RD del by del RD into RD del PD by del RD is equal to del PD by del PD. For RD is equal to 1, that means at the well bore PD becomes PD, the dimensionless forces become PD, T2 comma 1. This 1 is the RD for this point, and that will be equal to 2 pi Ks by Q mu Pi minus PWF. Okay. For allowing the presence of a mechanical spin factor, 2 pi Ks by Q mu Pi minus PWF is equal to PD, PD plus S. Okay, S is the spin factor. S is also dimensionless quantity, so it can be added or subtracted to dimensionless pressure. The reasons for using dimensionless variables are as follows: simplification and generality in mathematics. Okay, now the equations become a lot less complicated. Okay, if radial flow of any equation can be described by dimensionless analysis, the solutions will be the same regardless of the nature of fluid. Okay. And equations in terms of dimensionless variables are invariant form irrespective of the unit system used. Okay, so first thing we get rid of the unit system, and then since we are considering the dimensionless equations, right now we are looking at transient flow, okay, or semi-steady state flow. So the shape of the boundary and the location of the well and the nature of the fluid, we don't have to introduce separate variables for these. Okay, this equation and the solution of this equation will be applicable regardless the flow of the boundary, the shape of the boundary, the fluid nature, or the location of the well. Okay, and mathematics is simplified. Okay. Dimensionless variables are easier to deal with. The transient flow solution of the RD at RW at R is equal to RW is PWS is equal to Pi minus P mu by 4 pi kh ln 4 kT by gamma phi mu C RW square plus T. This is the simplified solution. Okay, this is the simplified solution, and accurate solution, instead of ln 4 kT by this thing, there would be a EI, exponential integral x. Okay, and this equation can be rearranged to get 2 pi kh by q mu Pi minus PW is equal to 1 by 2 ln kT by phi mu C RW square, that's TD, so 4 TD by gamma plus S. Okay, so we get PD dt is equal to 1 by 2 ln 4 TD by gamma, which is equal to 1 by 2 ln TD plus 0.809. Okay, and this is the equation that is valid only when we are considering the flow at well bore. Okay, because at well bore RD is equal to 1, so this can also be written as TD comma 1. Okay. For semi-steady state case, PWF is equal to Pi minus Q mu by 2 pi kh half ln 4A by gamma C RW square plus 2 pi kT by phi mu C. A is the area of the reservoir, areal extent of the reservoir, plus S. Okay. So 2 pi kh by mu Pi minus PWF is equal to 1 by 2 ln 4A by gamma CA RW square plus 2 pi kT by phi mu CA plus S. Okay, we have rearranged this equation, and then 2 pi kh by q mu Pi minus PWF will be Pt is equal to 1 by 2 ln 4A by gamma C RW square plus 2 pi kT by phi mu CA, and there would be a plus S also here. So another version of dimensionless time can be defined as TDA. Okay, this will be equal to TD into RW square by A. TD was dimensionless in itself, and here the dimensions are length square to length square. Okay, so again this is dimensionless, so this will be equal to KT by phi mu CA. Okay, now we will substitute this in the previous equation to get another form of relation between PD and DT, which will be PD is equal to 1 by 2 ln 4A by gamma CA RW square 2 pi T dA. Okay. Again, this equation is for flow at well where RD is equal to 1. That is why we are not seeing an RD term here in this equation. Okay, because RD has been kept as 1. So for where a well located at the center of a regular shape, the drainage area like a circle square. For a well located at the center of a regular shape, drainage area like a circle, square, hexagon, etc. The late transient period is extremely small. Okay. Why the late transient period is extremely small? Because the well is located symmetrically inside a regular shaped closed body. Okay. So that pressure disturbance that is created at the well, it will reach at the same time to all to the boundary in all directions. Okay, in all directions. Okay, and so that is why the late transient period is small. Okay, the late transient period is high if the well is not placed symmetrically at the center of the boundary, or the reservoir boundary is irregular. Okay, it is not a regular shape. Okay, so in that case, in one direction the pressure disturbance will reach before, and in other direction the pressure disturbance will reach at later time. So in such a case, the late transient period is longer. Okay. So in this situation, the flow equations for transient and semi-steady state periods can be equated to determine the approximate time of change from transient to semi-steady state condition. Okay, because for late transient we don't have a solution. Okay, that condition is too complicated, so we cannot find the solution analytically for late transient period. Okay, and not even numerically we cannot find a solution for the late transient period of RD. Okay, so if the late transient period is small, okay, and when will it be small? When the well is placed at the center of a closed boundary, and the closed boundary is a regular shape like a square, hexagon, or circle. So we equate the transient equation and the semi-steady state equation to find the time at which the flow or the pressure disturbance reaches the boundary. Okay. So for C is equal to 31, that was for the circular closed boundary, I guess. We get TD is equal to 0.1. So that means at dimensionless time, apical dimensionless time, TD is equal to 0.1, the pressure disturbance reaches the boundary. Okay, so that will be the time when the flow will switch from transient state to semi-steady state. Okay, while draining from a regular drainage area, there is an abrupt change from transient to semi-steady state, irrespective of the size of the area being drained. Okay, so regardless of what the area is, at TD is equal to 0.1, the flow will change from transient state to semi-steady state. Okay. Now we'll see the superposition theorem, which again is another very important foundation for well testing. Okay. So mathematically, the superposition theorem states that the sum of individual solutions of a second order linear differential equation is also a solution of the equation. This is the mathematical definition of the superposition theorem. Okay. So it says that the sum of individual solutions of a second order linear differential equation. Okay, so our radial diffusivity equation in dimensionless form, it was a second order linear differential equation. Okay, so sum of any two solutions of our RDE will also be a solution of the equation. Okay, so applying the superposition theorem means that individual constant rate wells can be placed in any position in the reservoir at any time, and an expression for the resulting pressure distribution in the space and time is derived by inspection. Okay, now this is the advantage of using dimensionless variables which we are talking about. Okay, the mathematics becomes easy. So like if we have a closed reservoir and there are different wells at different locations. Okay, and then we will have to find a solution for each well, a solution of RD at each well. Okay, but then what we can do is we can find a solution of those wells collectively. Okay, and even for a single well, it will be produced at different flow rates at different times. Okay, so if we use the dimensional form of equation, the RD as we know it, okay, we will have to derive a different solution for each time the flow rate is changed and for each well. Okay, but in case of RD, all the solutions are additive. In case of dimensionless variables, all those solutions of that RD radial diffusivity equation are additive. They can be added. Okay, so we add the solutions, we get a corrective solution of the radial diffusivity equation. Okay. So now I'll explain it with an example. So consider a well producing at a series of constant rates for different time periods shown in the figure. Okay. So initially the well was producing at rate Q1. At Q1 the rate is changed to Q2, and then at T2 the rate is changed to Q3, and at T3 the rate is changed to Q4, and so on and so forth. So at time Tn, until time Tn, the well is producing at rate Qn at any time Tn. And this is for a single well only. This is for one well. For one well we are changing the rates. So the pressure response at the well was PWF. That can be represented this way. We can get PWF. If there will be decline, then there will be build up, a little build up, and again decline, and then again build up. And the reason for that is here the rate is reduced, then the rate is increased again, then the rate is reduced further. Okay, and this is somewhere intermediate. Okay. So our objective is to find the bottommost flowing pressure PWF at T is equal to Tn when the well is producing at rate Qn. This situation can be visualized in the following way. A well 1 is drilled, which is producing from T is equal to 0 to T is equal to Tn at rate Q1. Okay, so the net withdrawal from the reservoir is Q1. Okay, another well 2 is drilled exactly in the same position as well 1. Okay, and this is hypothetical, this is a way of visualizing. Okay, so another well 2 is drilled in exactly the same position as well 1. It starts producing at a rate Q2 minus Q1 at time T is equal to T1. Okay, so this well 2, hypothetical well 2, starts to produce from the reservoir at time T is equal to T1, and it starts producing at a rate of Q2 minus Q1. Okay, so now the net rate at which the fluid from the reservoir is being produced, that will be equal to Q2. Similarly, at time T is equal to T2, another well 3 starts to produce from the reservoir. Now this time the rate of this well is Q3 minus Q2. Okay, So this process continues and more wells are drilled. At time t is equal to Tn minus 1, well n starts producing at a rate Qn minus Q1. So finally the net rate of production from the reservoir is Q1. Okay, and we have to find the bottom hole fluid pressure when the rate is Q1. Okay, so the superposition theorem applies to find a composite solution of the radial diffuse equation in dimensionless form 1 by RD del by del RD into RD del PD by del RD, which is equal to del PD by del PD. So for this solution, the composite solution of the above equation can be obtained by adding the individual constant rate solutions for the rate time sequence on the next slide. Okay, this is what superposition is. Okay, this is the step in which we are applying the superposition principle. Okay, we are adding the individual constant rate solutions of each of those hypothetical wells to obtain a solution for the well, for the total reservoir. Okay, so the rate Q1 is acting for time Tn, then rate Q2 minus Q1 is acting for time Tn minus T1. Okay, the sum of these two rates is Q2. Then similarly, this cycle goes on until we obtain a rate Qn. Okay, which will be acting at time Tn. So the solution for the equation was 2 pi kh into Pi minus Pw of n is equal to Q1 PD PDN plus SDs means this is the solution for the time when Q1 rate was there. Okay, then this is for the time when Q2 minus when well 2 was there, then well 3, well general random well Qj, and then for the finally Q1 minus Qn minus 1, Qd, Qdn minus Qdn minus 1 plus S. Okay. So we get the solution as 2 by kh by mu Pi minus Pw of n. Okay, this is what we wanted to find. Pi minus Pw of n is equal to j is equal to 1 to 1. Okay, it means basically j is equal to 1, that means 1 to 1 means the rate is being changed n times. Okay. So Qj minus Qj minus 1, Pd, Pdn minus Pdn minus Pdj minus 1 plus Qn S. Okay. S is for the steam factor. Okay. So our equation is called the basic equation for interpreting the pressure time rate data collected during any well test. This is the fundamental equation for any well test. Okay. The test is designed as the series of different flow rates, sum of which may be zero, so that the above equation can be interpreted to yield the required reservoir parameters, which are Pi, initial pressure, P bar, the average reservoir pressure, K permeability, S, the steam factor, A, the drainage area, and Ca, the least shape factor. Okay. And the well tests are of 3 types. The most common forms of well testing are single rate drawdown test, and then pressure build-up test, and then multi-rate drawdown test. Okay, and we will study these different kinds of well tests in subsequent presentations.